Welcome to the presentation on the topic of precision agriculture and education perspective. The first part of this presentation will discuss what I see as the challenges in teaching precision agriculture. And in the second half of this presentation, I am going to present or show a new sensor I have been involved in developing. My name is Dr. Nikki Cooley, and I am the coordinator of the Bachelor of Agriculture and Technology from Melbourne Polytechnic. This is a degree program that is delivered as a partnership with Latrobe University. The degree is separated into a number of majors, with the most populated being agronomy, aquaculture, and viticulture and winemaking. Degree programs pathways were compiled with significant inputs from associated agricultural industry, with the aim to mix both practical skills and an understanding of the theory that underpins these industries. In this program, we have subjects dedicated to the technological aspects of agriculture, and I'm going to talk about one of them specifically that we call future farming technologies. The uptake of technology in agriculture is both wide-ranging and diverse, from very little to technical feats of fully automated systems. The technology usually requires some level of scholarly understanding, which either comes from the farmer or via a consultancy firm, where this support is part of the business model. It is impossible to teach everything, so we concentrate on the following areas. The first topic we cover is that of technologies around gene transfer, gene manipulation and breeding in agriculture. A second topic that we cover is that of future technologies, where a student will explore the scientific literature and report on the likelihood and the logistics of a concept or early technology development, making it into a commercial viable tool. We cover models and modelling, and the topic I want to talk to you today is that of sensing and precision farming technologies. It is this topic and the challenges of teaching this topic I would like to discuss in detail. In the first part of this topic, I will teach our students about specific sensors and the background of sensing. In the second part of the topic, we bring this information together to explore the area of precision agriculture. Students will be taught by introducing the history of sensing. This will tend to set the context of sensing in agriculture. Students are then to explore the fundamental of sensors. They learn about sensing in GPS, they learn about climate sensing, soil, plant, animal, water and wine sensing. This gives the students an understanding of the range of sensors that are available. The students will also learn about the assumptions that underpin these sensors. For example, how does this sensor work? Are there certain conditions this sensor will not work in? We cover aspects of sensor calibration and installation where they are applicable. We also look at sensor data, how it is collected and how it might be transmitted or communicated. Students learn about systems of communication, such as wired systems versus wireless, and we also show examples of where that communication is mixed. Where applicable, we cover aspects of data, technical and/or electronic and communication standards. And we also review legislation and governance in this area where it might be applicable. For example, that in radio communication. Not every single sensor can be taught in the time frame that our subject affords, coupled with the observations that some commercial sensing systems turnaround is high. So you can find yourself in a situation that by the time you have taught a student about a sensor in the first year of their degree, by the time they graduate from the program 3 years later, the sensor is no longer commercially employed. Therefore, we concentrate on the basics of a sensor. What is in that black box? In a workshop, we couple sensor demonstration with sensor construction. The students construct or make their own sensors. Some make temperature sensors, while others might make a water or a soil sensor or a climate sensor, depending on their areas of specialization. This demonstrates how a physical signal is converted into a number or an output that we might use in farming. The students have to follow the wiring diagrams. They have to input sensor specifications into their design, and they have to set up a communication protocol, for example a wireless chip, or enable the communication via cable. They code the program, we help them with this, and it's usually a Java-based IDE program. And then they download the program into the sensor to set it up and start the sensors. This is based on the Arduino system. We can then use this technology to demonstrate the different methods of sensor types. For example, we might look at temperature sensing and compare a thermocouple method with a psychrometric measurement, with an infrared measurement or optics, and then compare that with a traditional wet bulb thermometer. Students have completed the sensor part of this topic. They then move on to applying their knowledge in the precision agricultural framework. We cover the theory, the assumptions underpinning precision agriculture, and then contextualize these into either a commercial or a research setting. I think it is important that the students can differentiate between these two objectives as they result in different systems. We then present a range of case studies to demonstrate this technology in more detail. I see the challenges in this area not being around the teaching of the fundamental of precision agriculture. We have many techniques and many systems in place to do this effectively. But what I do see as a barrier is to enable our students with the practical competencies that the industry considers important. What are these skills? What should degree students know about precision agriculture when they leave the degree and start working in the industry? How would our students take a suite of data like soil moisture as shown on the graph on the slide and convert that into profit increases? So I'd like to set a challenge to the industry. The challenge is, how do we deliver the skills and the practical competencies required for precision agriculture? The obvious answer, and perhaps the one that is used most extensively in precision agricultural courses, is that you demonstrate a commercial system that's already in operation. This exercise has many advantages, and one I encourage. Any farm or commercial PA application that will be able to demonstrate our students their systems would be great. So please contact me, send me an email, because I'd love to hear from you, and I'd love for our students to come out and see your system. But not only seeing the system, I want our students to have competencies further than this. I want them to be able to use a precision agricultural systems in their area of interest or expertise, whether this be a high specification vineyard or an agronomy enterprise optimizing plant density or fertilizer applications, or whether it be using PA to enable weight gain in fish farming. I want our students to be able to be practiced in these skills. I welcome any feedback from your members on how we could develop these skills. An idea I had that I'd like to explore with you today is to perhaps set up an incubation unit within the subject. The aim of this unit would be to deliver high qualified skills in PA. In this incubation unit, industry, education and students would work together to enable their skill development. I would like to see their skill development centered around solving an industry problem, as this helps to contextualize what they are learning. Brings us to the second part of this presentation on the Sensor Development Initiative. I have been working in a small group of scientists that comprise of physicists, optics experts, mathematicians, and engineers. We set out to understand water stress in plants better and were hoping to optimize irrigation practices by having an automated real-time sensor. We felt at the time when we started this investigation that the current technology either measures the plant by physical interaction, that is, you have to remove a part of the plant to get your analysis, called a destructive harvest, or that it estimates the water use by an indirect measurement like soil moisture or modelling such as evaporative transpiration calculations. These methods all have advantages and disadvantages, but I was aiming to develop a direct measurement of plant water use that was both dynamic in its nature, but did not connect, alter, or require a destructive harvest of the plant. I wanted to utilize this sensor to inform and improve automated irrigation scheduling, or smart sensing. What we ended up developing was a sensor that was able to detect and determine plant surface entropy. It is technically wave band specific entropy of the leaf surface that is being detected. This gave the research team some incredible insights into what is happening to plants. For example, when a leaf goes from a light to a dark environment or vice versa. We see topographical changes before the mechanism of transpiration has had a chance to even be activated. Therefore, we have concluded that leaf topography is very sensitive. We have got to the stage where we have developed the technical aspects of the sensor. That is, we have a prototype. We have published in a suite of engineering and optic journals the fundamentals that underpin this technology. And we have set up some basic correlations with plant stress, some of which I will present here. The first figure on the slide, figure 1, demonstrates the correlation between day versus night. This demonstrates that plant surface topography is different during the day than it is at night. The second figure shows that surface topography changes over time, and these changes can be tracked. These observations are important as they indicate that surface topography can act as a mirror or an indication of the internal processes within the plant, and it can do this in a manner that we were perhaps not aware of previously. And secondly, it begins to demonstrate the dynamic nature that can occur within plants.